Greetings, math fans. All right, so this is worksheet 2, and we're finding the limits of all these different functions, and it even says do not use your graphing calculator. The last two, you will use your graphing calculator just to kind of compare your using your graphing calculator with doing it by hand. Okay, so our main goal here, math fans, is to allow the number to be plugged in directly using some of our identities or using to maybe factoring a little bit, whatever it is, because once we can manipulate it and plug it in directly, we're good to go. Okay. Obviously some of these are going to be undefined if you actually do a value at that point, but we're doing limits, which means we're approaching it. Okay, that's really, really important. So let's just kind of get started here. The first one, it says limit as x approaches 0, sine of x over 5x. Remember, our goal is to get that to be sine of 5x over 5x. Okay, and then we're good to go here. And so obviously you can't change that sine of 5x, but what I can do is I can move this guy out. So I can do 1/5 limit x approaches 0 of sine of x over x, which then, of course, this limit, as we know, it's one of our identities here, is just 1, so the answer is 1/5 times 1, which is 1/5. Okay. Next one, again, this is pretty easy, right? I'm just going to do limit as x approaches 0 of 3 parentheses cosine of x minus 1 over x. Then I can pull that 3 out, so it's 3 limit x approaches 0 of cosine of x minus 1 over x is 3 times 0, because that equals 0, cosine of x minus 1 over x, and the answer then is 0. Alright, guys, you got to show me this step here, right here. You got to show me this. Because if you don't, and you just say, oh, it's equal to 0, you're going to lose a point for that. Alright, because you have to show me, just got to show me all your steps. Alright, this next one, well, it's a little more complicated because you're looking at it and going, wait, we don't know anything with secant. But come on, you should almost look, what does it kind of look like? It looks like cosine. So let's just do everything in terms of cosine. So it's limit as theta approaches 0 of, we're just going to do 1 over cosine theta minus 1 over theta 1 over cosine of theta. Okay, and then I can let's multiply this by cosine theta over cosine theta, right, to get rid of that complex fraction there. We got limit theta approaches 0 of 1 minus cosine theta over then these just cancel out, right? So we have theta. Oh, look at that, man. Oh, it's so sweet. All right, so we're almost there. Remember, this is not something you can use directly here. 1 minus cosine theta over theta. You need to write that as limit as theta approaches 0 of negative, and then it's cosine theta minus 1 over theta, which is negative limit as theta approaches 0, right? The negative comes out by our constant multiple rule, and we get cosine theta minus 1 over theta, which is negative 1 times 0, which is 0. Okay. Next one, I'm just going to write in terms of sines and cosines. So limit as alpha approaches 0 of cosine of alpha, sine of alpha over cosine of alpha over alpha. Okay, those cancel. So we get limit as alpha approaches 0 of sine of alpha over alpha, which is of course equal to 1. Okay. This one, you guys should recognize limit as x approaches 0. I can break that up to sine of x over x times, right, by product property, limit as x approaches 0 of sine of x over x times limit as x approaches 0 of sine of x, right? Just kind of broke that sine x to cubed, sine x, sine x, sine x, and then of course that's 1 times This one's direct substitution, and sine of 0 is 0, so our answer is 0. Okay, but you got to show me all that work. This one, again, looking a little complicated, but remember I told you guys if you can do direct substitution, do it. And I can totally do direct substitution. And so limit as theta approaches pi, that's just pi times secant of pi. And I can do direct substitution because, remember, secant goes with cosine, and cosine of pi, right? Cosine of pi, we're over here, is -1. So it's pi times -1 equals -pi. Okay, not bad. I'm just going to rewrite that. Limit as x approaches pi over 2 of cosine of x over cosine of x over sine of x, right? And however you want to do that, if you want to multiply the top and the bottom by sine of x, do that. Right? And then this guy cancels, and you end up getting cosine of x over, or times sine of x over cosine of x. That cancels. So I really just have limit as x approaches pi over 2 of sine of x. And what's the sine of pi over 2? It's equal to 1. Okay. Let's go to the next one here. I've got 7 sine of 3x over x. Again, I can't do direct substitution, but you can see this guy right here is going to be one of our identities. That means I just multiply this by 3 and 3 on the outside. Do you guys agree with that? So it's really 3 limit as x approaches 0 of 7 sine of 3x over 3x. Okay, that makes sense, everybody? And then what I can do is I can even pull this guy out too. So really I have 21. This is what I want. 21 times the limit as x approaches 0 of sine of 3x over 3x. So it's 21 times 1, which is 21. Ew, 21, blackjack. Oh, sorry. No gambling. Okay. Next one, again, can't do direct substitution. What I can do is I can do a little factoring here. First of all, that 2 minus x, I'm going to factor out. If I flip it around, I can do negative parentheses x minus 2. You guys agree with that? And at the bottom, I can do x plus 2, x minus 2. Those cancel, and I have limit as x approaches 2 of -1 over x plus 2, and now I can do direct substitution, so it's -1 over 2 plus 2, which is -1/4. Okay, this next one, again, I can't do direct substitution, so let's do a little factoring here. Limit as x approaches 1 of x plus 2, x minus 1 over x plus 1, x minus 1. That cancels, and now I can do direct substitution. So I get 1 plus 2 over 1 plus 1. So I get 3 halves. Okay, pretty straightforward. Let's keep going here. Very similar to what we need here, right? It's tangent squared of 2x. Ignoring the squared for now, I'd like to have a a 2x in the bottom here, right? And let me write it this way. Limit as x approaches 0. How about if I do this? Tangent of 2x over x times limit as x approaches 0 of tangent of 2x. Do you guys agree with that? Okay. And I just need a 2 here. So do you guys agree I can put a 2 here and a 2 here? Okay. And you're like, well, what about the others? What about the right-hand side, Mr. Curvis? And I would say, I can just do direct substitution. Can't you? Sure, there's no denominator. It's only when you have a denominator the 0 where you have to kind of manipulate things a little bit. So anyway, for this first one, I have 2 times, what's that limit? Well, isn't that just 1? Because tangent of 2x over 2x. And then it's times, and what's, it's the tangent of 0, right? So it's 2 times what's tangent of 0? It's 0. So that equals 0. Okay, but you got to show me all that work. Next one. Well, again, I can't do substitution here, so what I'm going to do is let's FOIL that top guy out there. Because what's going to happen, our goal really, math fans, is to get rid of that denominator. Okay, we don't want it to equal 0. So if I FOIL that top part out, I get x squared plus 2xh minus, or plus h squared minus x squared all over h. Well, that's pretty sweet. The x squareds cancel. And I have, so I forgot limit here. Limit as x, or h approaches 0. Got to write that each time. So we get limit as h approaches 0. And I have 2xh plus h squared. So I can factor out an h. Sweet! Cancels. Now I can do direct substitution. So as h approaches 0, I get 2x plus 0. My answer is 2x. Okay? Not too bad. Let's keep going here. You guys should recognize number 13. Limit as x approaches 5 of 9. I'm saying what, as x gets closer to 5, what happens to y? Well, it's equal to 9, right? So that's your answer. Equal to 9. Okay, this next one, we're going to multiply the top by the conjugate, top and the bottom. So you get root 3 plus x plus root 3. Okay, that gives us limit as x approaches 0 of 3 plus x. Remember, the outside inside cancel, and then we get minus 3. And I'm not going to distribute the bottom because it's just going to make things very ugly. And what happens is the 3's cancel on top, so I get limit x approaches 0, and we just get x over x times square root of 3 plus x plus root 3. X is canceled there, and I can do direct substitution because that's just a 1 here. So you get 1 over 3 plus square root of 3 plus 0, so square root of 3 plus the square root of 3. So you get 1 over 2 root 3. Rationalize, you get root 3 over 6. Okay, not bad. 15 is the same thing. Multiply by the square root of x plus 2 plus root 2. So you get limit as x approaches 0 of x plus 2. Outside inside cancel. Minus 2 over x times x plus 2 square root plus root 2. Okay, so that cancels, and we wind up getting limit x approaches 0 of x over x square root of x plus 2 plus square root of 2, and they cancel. So then I can do direct substitution, and I get 1 over 0 plus square root of 2, which is square root of 2, plus square root of 2. So it's 1 over 2 root 2, rationalize, which gives us root 2 over 4. Okay, not bad. This one, similar to one of the homework problems we had a while back, but basically I'm going to multiply, I want to get rid of the fraction. Okay, I want to get rid of that ugly complex fraction, so I'm going to multiply everything by 4 times x plus 4 over 4 times x plus 4, right? Okay, because I got a 4 plus x, or x plus 4 here, and a 4. So if I do that, I get limit as x approaches 0. If I multiply the first one, the x plus 4's cancel, and I just get 4 minus the 4's cancel, and I get x plus 4. In parentheses, don't forget that, otherwise it gets nasty. In the bottom, I just get 4x times x plus 4, right? So I distribute that I get 4 minus x minus 4, and I just wind up getting negative x. And the bottom I get 4x, x plus 4. I'm not going to distribute that because now I can see the x cancels, which is perfect because now I can do direct substitution. So it's negative 1 over 4, and then I put a 0 in there. Sweet. So it's negative 1 over 4 times 4, or negative 1 over 16. Okay? Alright, so the next one, and you look at it and you go, oh man, it's direct substitution, or you don't think direct substitution, you think, oh, I gotta do all kinds of nasty stuff, but this is direct substitution. Sweet. So it's just 3 plus 1 minus 2 over 3 plus 3. Okay, that's a pretty easy problem. So it's the square root of 4, which is 2. 2 minus 2 over 3 plus 3. So it's 0 over 6, which is 0. Okay? Use your graphing calculator to complete a table of values in order to estimate the limit of each of the functions. Verify your estimate by determining the limit algebraically. Okay, so let's just take a look at what the graphing calculator, if you use your to make a table, we can just type this in our graphing calculator. Okay, then I'm going to bring up my graphing calculator here. And we're going to go y equals, put a parenthesis on top. So it's going to be the square root, so second x squared, square root of x plus 5. And it's a new operating system for this one, so I'm just going to cursor over here a little bit. Minus the square root of 5. Okay, cursor over again, and close the parenthesis. And I divide by x. Okay, and then let's just do zoom 6. All right, see what's going on here. Well, let's see. It kind of looks like a straight line on this guy here. So can I zoom? Let's just zoom in a little bit on that, just to kind of see what's going on. Okay, and of course we're seeing what's going on when it's getting closer and closer to 0. So I can do trace, and x is equal to 0. Of course, is undefined, but let's cursor a little bit away, and that's why you can come up with your values here, right? What's to see what's going on as you get closer and closer. But if my calculator right before it gets to x equals 0, it looks like it's 0.223. Now let's see what's going on the other side. 0.223. And 0.224. Okay, so I'm going to say roughly this is 0.223. So it's a decimal answer. So let's do it mathematically now. Let me erase this right here. Right on top here, 0.223. If I do it mathematically, of course, I'm just going to multiply the top and the bottom by square root of x plus 5. Plus the square root of 5 over square root of x plus 5 plus square root of 5. Okay, by the conjugate, so you get limit x approaches 0, and then you get x plus 5, outside inside cancel, minus 5, all over x times the square root of x plus 5 plus square root of 5. Okay. And so I get limit as x approaches 0 of x over x times square root of x plus 5 plus square root of 5. The x's cancel, and I can do direct substitution. So I get 1 over the square root of 5 plus square root of 5, which is 1 over 2 root 5, and I rationalize. So I get root 5 over 10. Alright, and let's see what that is on our graphing calculator to verify that. So let's quit out of here. The square root of 5, with your cursor over, divided by 10, should be something around 0.223. And hey! Yay! Okay, it is 0.223 or 0.224, right? So again, you know, how accurate you want to get is just depending on how close you're getting to 0 for x value. Okay, let's do the last one here. So it's I can manipulate the top a little bit here, right? You guys are great can factors, so I can do limit as x approaches -1. I can factor the top to x plus 2 times x minus 1, and the bottom x plus 1. Okay, there's nothing to cancel here, so that's kind of a bummer, right? I can't cancel anything. So truly what's going on here is if I can't cancel it, it's not a whole. So it's actually, do you guys agree that this guy right on the bottom here, I have a vertical asymptote at x equals -1. Well, I'm trying to approach x equals -1. So what? Let's take a look at our graphing calculator. What's going on here? Okay, so let's put this in here. So let's clear this out of here, and I'll put it in just the way it is there. I'll put it in parentheses, so I have x squared plus x minus 2, close parenthesis, divided by parentheses x plus 1, close parenthesis. Okay, let's do zoom 6. Very interesting. Very, very interesting. Okay, so we actually have an oblique asymptote, don't we? You guys should kind of recognize that from Algebra 2 from last year. But there's an oblique asymptote. So when x approaches -1, let's go from both sides. When it's approaching -1 from the left-hand side or from the negative side, do you guys agree it's going to positive infinity? And when it's, so let's actually write this down here. Limit as x approaches -1 from the positive side of that function. Okay, let's look at that again. When it's approaching from the positive, or from the positive side, it's going to negative infinity. When it's coming, so from the positive side equals negative infinity, right? Take a look at that again here. And when it's coming from the negative side, it's going to positive infinity. So limit as x approaches -1 from the negative side is positive infinity. So what does that mean, math fans? This limit does not exist. Do not eat. Okay? Because the two-side limits are different. Two one-side limits are different. That means the two-side limit does not exist. Okay, so that's it, math fans. Just a little. This last one was a good example of, it doesn't always exist. You can't always cancel things out. But that's it. All right, math fans. Have an outstanding day. Adios. Goodbye.